Alright, so this PowerPoint will be covering the findings of Lab 3. The purpose of this lab is to use our knowledge of magnetic fields to determine not just the strength of a magnet's dipole moment, but the relationship between distance and a magnet's produced field. By carefully aligning a magnetometer, which in this case was from our cell phone, with the Earth's natural magnetic field, and then placing a magnet perpendicular to said field, we can actually measure with relative accuracy the strength of the field produced by just the magnet, as well as the corresponding distance. With this data, we can establish an overall trend and come to some conclusions regarding our magnet's behavior. This is actually a screenshot of all of the data we took for this experiment. We found the distances at which our magnet produced a field of a target strength and took multiple samples to average out the data and be as accurate as possible. And this table sums up our data by giving us the average distance and corresponding field strength of our targeted magnetic fields. Now, if we represent the strength of the magnetic field as some constant times the distance to the power of n, we can rewrite the equation such that we can find both the value for k and n if we plot our data accordingly. Using and plotting the data from our averages table, we came up to a value of roughly -3 for n and -14.28 for k. If n is roughly equal to -3, that means that the strength of the magnetic field is inversely proportional to the distance, meaning that as our distance gets bigger, our electric field gets weaker. This is consistent with our knowledge of bar magnets, where as you get closer the strength of the field increases. However, this also means that if you were to say double the distance, it would only be an eighth as strong. And if we compare our value found with the actual equation for the strength of a bar magnet along its axis, we found that we were off by less than 1%. As far as finding the dipole moment for our magnet, we can set our original equation of k times r to the power of n equal to the actual magnetic field equation for a bar magnet. Doing this allows us to eliminate the r's from the expressions, since our calculated value and theoretical value are nearly identical. Then it's simply a matter of rearranging the remaining items to give us an expression for mu, which in our case was found to have a strength of 3.142 amp meters squared. Now, some key observations to be made during the experiment are both in relation to distance, in that as the bar magnet got closer to the magnetometer, the x component of the magnetic field increased, and likewise as the bar magnet got increasingly further away, the x component approached zero. Both of these make sense, since we now know that the strength of the magnetic field was inversely proportional to the distance. To answer some what-ifs about this experiment, what if we hadn't chosen to conduct our experiment on the x-axis of the Earth's magnetic field? Well, if we had chosen to lay the meter stick down at any angle other than perpendicular to the Earth's natural magnetic field, north specifically, it would have offset all of our results. More importantly, it would have made it significantly more difficult to observe the magnetic field produced by the magnet, since its magnitude would be split into an x and y component. Also, none of our graphing tools to get our values for k or n would work. And what if we were to have stuck two identical magnets together? How would that change our results? Well, if we had chosen to do that, we would have still observed the same relationship between a bar magnet and the magnetic field produced at a distance. However, we would have observed a larger dipole moment. The purpose of the glow script model in this lab was to compare the theoretical strength of the magnetic field at a 45-degree angle with the measured values that we also took. It also shows the magnetic field at 6 equidistant locations around the magnet to show the behavior of the magnetic field vectors around the bar magnet. This is a screenshot of the produced glow script model. Note that the text box does actually give the location of all 6 vectors as well as the magnitude of the 45-degree angle vector. This is just a breakdown of how we placed the phone for the 45-degree vector. And this is all the data we took at that 45-degree location. Note that we actually had to compensate for the Earth's natural magnetic field, which we did by subtracting its value from our measured y components. Something we would not have been able to do had we lined up our phones and meter stick any other way. And also, if we compare our measured values with our theoretical values, both our x and y components are off by less than 40%, which really isn't bad considering how small these numbers are. And this is just a screenshot of all of my code for the model. And this is the last of it. Thanks for watching.